Welcome back to Computer Science 3200. Today, we are going to have the first of two lectures on the subject of game theory. And this isn't necessarily exactly tied into AI, but it is tied very deeply into the notion of decision making, which AI is also tied into. So I like to teach a little bit of game theory when I teach AI. And not only, in my opinion, does game theory help you make computer-related decisions or, making a machine to make decisions, but game theory really teaches you to think strategically in real life as well. And not enough people are taught about game theory. I think basic game theory should be taught in like high school because it's very important. So these two game theory lectures will sort of give us the motivation for why this minimax algorithm is as good as it is. So we'll be talking about game theory today. We will be playing a game later in the course, and then we'll be playing it again, later in the lecture, and then we'll be playing it again in the next lecture to see how our answers change as we learn a little bit more about game theory over time. So stay tuned to the lecture because we'll be playing a game. I'll be sending out a link to a poll which you'll answer, and then we'll see who ends up winning that. And of course, if you're watching the recorded lecture of this, then the poll has expired. So you'll just feel free to have a look at the results. So let's go over here to the PowerPoint and let's get started. So Computer Science 3200. Lecture 8, Intro to Game Theory, Part 1 of 2. So what is game theory? Game theory is a set of mathematical models and algorithms for decision making. So it's an analysis of strategic actions in scenarios which can be defined as games. It has many, many uses in not only like mathematics and computer science, but in social sciences, economics, and in my opinion, just everyday life. Oops, sorry. I've got to turn off my phone notifications. Sorry about that. So game theory is not only about games. In fact, I would say that the discipline which makes the most use of game theory is actually economics. They use game theory at a very deep level in economics and also in certain parts of mathematics as well. And the weird thing is, in life, we teach people, as teachers and professors, we teach people like a lot of facts, like which tribe owns this piece of land, or which person was the wealthiest, or who went to the moon first. And we teach you algorithms and like mathematical formulas and stuff. But when it comes to like actually making decisions in real life, there's not really a lot of that going on in your school education, which is a little bit disappointing, right? Now, this isn't saying like how you should think politically or in your stance on socioeconomic issues or stuff like that. It's not telling you how to think, right? It's telling you the process, like one of the processes that you should consider going through when you go to make decisions, right? And ideally help us also explain how some other people make decisions and how we can come to terms with that. So let's teach this through examples, all right? We're going to have examples right out of the gate. So let's look at something that's called the grades game. So the grades game is where two players, okay, so two people, let's say two students in a class, maybe you and your friend, maybe you and someone that you don't know. So two players secretly and simultaneously make a choice with a defined outcome. So the choice here is that you're either going to choose alpha or you're going to choose beta. So both of you would like secretly and simultaneously write this down on a piece of paper, and then you'll hand it to the game master and maybe that's the professor or the teacher in this class, to get the outcome of the game. So the outcomes of making this decision are going to depend on what both people have chosen, all right? So let's say that you choose alpha and they choose alpha. So you've both chosen alpha. In that case, you're going to get a B-. if you choose alpha and they choose beta, you're going to get an A. If you choose beta and they choose alpha, you're going to get a C. And if you choose beta and they choose beta, you're going to get a B+. So out there in the chat, if you're participating and following along, just write down either A or B for alpha or beta, which of the ones you would choose in the following situation. Okay? Now, trust me when I say there's no right or wrong answer to this. We are going to learn the things that we would do in this course, right? But you can start to make some sort of guesses at like the way you would think to make this sort of thing. Like you say, okay, let's look at our two choices for alpha. We could either get a B- or an A, right? If we choose beta, we could either get a C or a B+, right? So a lot of people out there are choosing alpha. The reason which maybe there's like a lesser variance or like the highest one is higher, right? So the highest one is higher here, the lowest one is lower here. So we'll see going forward how we can apply some analysis to this rather than just sort of guessing at which one. So a lot of people out there are choosing alpha with a few betas. All right. So let's write this down in a more mathematical way. Okay, so we had both of our choices and both of their choices, right? So we can choose alpha, they can choose, or we can choose alpha or beta, they can choose alpha or beta. So let's write this in a table. So what this table represents, these two values here, those are my choices, and these two values here are the partner's choices or the other person's choices. So if I choose alpha and they choose alpha, I get a B-. If they choose beta and I choose alpha, I get an A. If I choose beta and they get alpha, or they choose alpha, I get a C. If I choose beta and they choose beta, I get a B+. So that is another way of writing that down in a more compact, tabular, easy to digest and easy to formulate form, right? It's the exact same outcomes as this, but it's just in tabular form, which makes it easier for us to write. Similarly, we're going to write down the partner's grades, okay? So, again, if I make these choices and they make these choices, essentially, if we both choose alpha or both choose beta, well, I'm going to get the same thing as they are, right? But if I choose alpha and they choose beta, well, I'm going to get an A and they're going to get a C, right? Because that's essentially the same as them choosing beta and me choosing alpha. So in this table here, I'm writing down what I receive if we make these choices. And in this table here, I'm writing down what the partner receives, what the other player receives if we make those choices. So if I combine both of those tables, I can have a single outcome matrix for this grades game. And it means that if we both choose alpha, we both get a B-. If we both choose beta, we both get a B+. But if I choose alpha and they choose beta, the first one here, that's my outcome, okay? So I'll get an A, but they'll get a C. And if I choose beta and they choose alpha, I'll get a C and they'll get an A. So just take a time, pause this if you're watching the video, and just figure out what this means and where everything is in the grid, okay? So again, my choices here along the side, partner's choices along the top, and in each cell, the first entry is what I will get, or this person over here will get, and the second entry is what they will get, or the person on top will get in the outcome matrix. All right, so that's what that means. The rest of the lecture will depend on this structure. All right. So, in the grades game, what do we have? So far, we have actions, right? So the actions are choosing alpha or beta. We have strategies. Strategies are a collection of choices for both players. And we have the outcomes. But this isn't yet a game that we can numerically evaluate. So what do you think that we're actually missing from this so far? So what's sort of missing from this outcome matrix? What do you think? So if we're trying to like win or lose this game, What is sort of missing from this matrix? And please put some answers in the chat out there. Someone says win condition. Someone says probability of opponent choice. So we're not talking about probability here. We're talking about, like, you know, you get to make whatever choice you want. So there's no probabilities. This is just telling you what happens if a certain thing happens. Someone else says point system. So point system and win condition are a little bit related, and they're pretty close to the thing that we're missing, okay? So what we have so far is we have, like, I'll get a B minus, I'll get an A, they'll get a C, but, like, we can't really evaluate that into, like, a winning condition or an amount of points, right? So what we need is we need payoffs. So in game theory, these are called payoffs. It's essentially our points, right? So what is the objective that we want to achieve in the game? So game theory can't help you decide your objectives or payoffs. But if you do have payoffs, game theory can help you achieve them. So for example, maybe in real life, we care only about our own grades, right? But maybe we also care about each other's grades. So what we have to do is we have to somehow assign these outcomes, which is the grades we would get, to a payoff, which is a numerical number that we can try and minimize or maximize. And so what I tried to say on that last slide is that game theory cannot help you translate outcomes into payoffs because that's a personal thing, right? However, if you have payoffs, just adjusting my camera here, if you have payoffs, game theory can help you make the decision, all right? So here's some payoff examples. So a payoff is assigning a numerical value to an outcome. So it's essentially, how much do I like the outcome here? So the more I desire that outcome, the higher that I would put the payoff. So let's make an example here. So imagine that one of the players is kind of greedy, and they're just going to assign higher payoffs to if they do better than the partner, right? So they want to kind of win the grades game. If they do better, that's all they care about. So, for example, a B minus is kind of a middle of the road grade. So if they get a B minus, the payoff is neutral. It's just like, it's a 0. But if they get an A and you get a C, then they looked at as a good payoff. So let's just call it 3. Okay? So 3, you know, higher than 0. Not a million, but we're just going to assign values to it. So now what we have is we had before the grade results matrix, but we've assigned some values to that based on the assumption that someone might be greedy. So this is a greedy person, and then that greedy person has translated the grades results into a payoff matrix, okay? So the payoff matrix is just a numerical assignment of outcomes to numbers. So over here, if I choose alpha and you choose alpha, we're both getting a B minus. That's kind of a neutral grade, so we're both going to get 0. A B plus is a little bit better, right? So I only really care about myself. So if I choose beta and you choose beta, that's supposed to be a beta there, then we both get 1 because we get a B plus instead of a B minus. But if I choose alpha and you choose beta, well, I'm going to get this A, which is better than a B plus, right? So I'm going to get a 3. However, down here where I choose beta and you choose alpha, I'm going to have a -1 payoff because I'm going to get a C and I don't want a C, right? And similarly, the other person is going to get a -1 up here because that's where they got the C. So we're just taking the grades results and we're translating them into a payoff matrix. And now this is not the goal of game theory to create payoff matrices, okay? This is just an example where I've taken like a real world sort of example and translated that into payoffs based on the assumption that someone might be greedy. So these numbers are completely made up and arbitrary, but the point being that once we have numbers, game theory can take over and start making decisions for us, okay? So here, the numbers are called utility. And players should attempt to maximize utility. That is like the number one rule in life, is maximize your utility when it comes to game theory, okay? So again, in this example, if I get a B minus and you get a B minus, that's a 0. If I get an A and you get a C, that's a 3. So the player really only cares about themselves, right? They don't care that you got a C. They're not sad about that. They're just happy that they got an A. So, in this case, if we have these payoffs now, what should you do? So write down in the chat now, if you have this, what would you do if, what choice would you make, alpha or beta, now that we have these payoffs? Okay? What would you do now that we have those payoffs? All right, we got a 50-50 split of alpha and beta in the chat. That's interesting. All right, so we've got more alphas coming now. So some people are asking, what is our goal? Our goal is to maximize our own utility. All right, so we are maximizing our payoff, maximizing our utility, because the payoff matrix here reflects our goals in life, right? So we have somehow had a magic formula that translates the outcomes to payoffs. And these payoffs, we are assuming that these reflect our true goals, right? So this is the payoff of a greedy person. So we're just assuming for now that we're greedy. And we've still got about a 50-50 split between alphas and betas. So that's it. That's cool. A few more alphas though. So what we're going to do, in order to decide what to do here, we're going to go kind of backwards. So this might not be intuitive at first, but this is the way that game theory sort of teaches us to make decisions. And what it does is it says, for each possible decision that the opponent could make, look at the outcome of our possible outcomes, right? So let's say now that we're going to look at if the partner chooses alpha. Okay, so let's look at what happens there. So if the partner chooses alpha, so assume for a second that they're going to pick alpha, right? So if you pick alpha, you get a 0, right? Because that's right here. And I apologize in advance for my bad circles drawing with my mouse. So if they're choosing alpha, if you choose alpha, you get 0. If you choose beta, you get -1. All right? So see how that works? That's what's happening. The first one over here, that's the one on the left, that's where I get my values. If the partner chooses beta, so now we're looking at this column where the partner has chose beta. Again, look at all of my possible choices. So if I choose alpha, I get 3. And if I choose beta, I get 1. So that means that if they choose alpha, then my choice of alpha gets a bigger result than my choice of beta. And if they choose beta, my choice of alpha gives a bigger result than my choice of beta. So alpha is always the best choice here. So no matter what they pick, I am going to get a better result if I choose alpha. Okay? Now keep in mind that that is only the case in this specific set of payoffs. If you are not a greedy person and you assign different numbers, you might get a different result. But again, game theory assumes that we have this value here. So a lot of the time in economics, you're going to put in like the number of like profits, profit margins and all this kind of stuff where it's kind of numerical to begin with, right? But what we've done here is we've just created an example matrix, and we have shown that if they choose anything, alpha for me is always better than beta. There's no reason I would want to choose beta because it always does worse than alpha. So if you didn't get that right the first time, that's okay, right? That's what we're here for, is to teach you this sort of level of mathematical decision making. So this introduces the concept of strategy domination. And by the way, any slide in this is great exam questions. So we say that a strategy, alpha, strictly dominates a strategy beta if my payoff from alpha is strictly greater than that of beta, no matter what the other players do, right? So that means no matter what the other player does, alpha is always better. And so in that case, alpha strictly dominates beta, okay? So the rule here is do not play a strictly dominated strategy, because the strategy that dominates it is better in every possible case, okay? So if you see here that alpha always performs better than beta, the rule is never play beta, because there's no point to. You'll always do better from playing alpha. Okie doke. Now, some of you may have already drawn the link between this game, the grades game, and a game called The Prisoner's Dilemma. So who out there has heard of The Prisoner's Dilemma so far, or before? Because it's very closely related, and we can use game theory to analyze the Prisoner's Dilemma game. So if you've never heard of the Prisoner's Dilemma before, if you want a refresher, we have two prisoners who are in separate cells. And the guards are basically, you know, so the police have caught these two people, and what they're trying to get to happen is they're trying to get them to confess or rat each other out, right? To say, yeah, it was the other guy, or yeah, we did it, or no, we didn't do it, right? The police want them to make a confession. And their level of cooperation is going to depend, is going to determine their sentence in prison, right? So here's what's going to happen. If neither of them tell on each other, well, the police have no evidence to go on, but they're kind of mad because no one told the truth, right? So they don't really have the perfect evidence, so they're only going to go to jail for a year, right? So if nobody says anything, they both keep their mouths shut, they both go to jail for a year. If both of them tell on each other, then they're both going to go to jail for 2 years because they have more evidence now, right? They both told on the other person, but at least they told the truth, right? So if they tell the truth, they're not they have more evidence of the crime, but they told the truth, so they just get a little bit more jail time. However, if one person tells and the other person doesn't, then the teller is going to get a bonus for cooperation, and the other one is going to get a harsher sentence for lying. Okay? So if one tells and the other doesn't, then the teller is going to go free, and the other one is going to go to jail for 5 years. All right. So this is the outcome. The jail time is the outcome. And let's just say, for example, that our payoff, our utility, personally, is a 1-to-1 direct correlation with how long we spend in jail, right? So this is the payoff matrix. If we just take the number of years in jail and make that a negative payoff, right? Because, I don't want to be in jail. I don't know about you, but I would certainly assign a negative payoff to that. So if we both tell, right, we have, we both go to jail for 2 years. If we both stay silent, we both go to jail for 1 year. However, if prisoner one if prisoner one stays silent, prisoner two tells, well, prisoner one is going to jail for 5 years, and prisoner two is getting released. Similarly, if prisoner one tells on prisoner two, and prisoner two stays silent, then the teller, prisoner one, is going to get released, and prisoner two is going to go to jail for 5 years. So that's how we take the English level outcomes of this word problem and translate it into a game theory payoff matrix. All right? A great example of an exam question. So, what do we do as prisoner one? If you are prisoner one, do you tell or do you stay silent? Which one are you going to do? All right, so let's apply the same logic that we had last time, all right? What we're going to do as prisoner one is we're going to sit there in our cell and we're going to analyze every possible action that the other person could do, right? And for everything that they could do, we're going to go down the list of the things that we could do and analyze our outcomes. So let's say now that we're looking at prisoner 2 is going to tell. So we are in this column of values here. So if they tell, well, if we tell, we get -2. If we stay silent, we get -5. So if they tell, us telling is better, right? If prisoner 2 stays silent, so now we're in this column. If we tell, we get 0. If we stay silent, we get -1. So telling or ratting the other person out strictly dominates not ratting them out. Okay? So that is the answer to this exam question, that in the prisoner's dilemma with this payoff matrix. Now, if there's a different payoff matrix, then maybe telling does not strictly dominate staying silent. Okay? So, so there's an important thing that someone just mentioned in the chat. So someone says, tell obviously because it is a less combined sentence. That is not the correct answer from a game theory point of view, okay? Because if you cared about combined sentence times, then that would be reflected in your payoff matrix. That would already be here, right? So if you cared about combined times, then your payoff matrix would be like the sum of both of the times, right? But that's not what we have done here. We have assigned values to the prison sentences only according to what we would get, because we're greedy criminals, right? If you cared about your partner's time in jail, then you would have a different payoff matrix. So just keep in mind that it's very important that whenever we are dealing with a numerical payoff matrix, these values are the only things that we care about, because they already reflect our philosophical view of life, okay? So just make sure that you never answer on exam question anything other than maximizing your own utility for this. Okay, that was a good point though, because it's easy to think that way, but just realize that the payoffs already encode all of that information. So game theory can't help you make the payoff matrix, but it can help you solve the payoff matrix once you have it. And so this person also said my own combined score, not just the other person's. It's incorrect, unfortunately. So that is not how you would go about solving this, because there are cases where the sum of all of your payoffs, the answer that has the sum of all the payoffs could be as higher, could not be a dominating strategy, okay? So just keep in mind that that is not the correct answer in game theoretically speaking, all right? And again, if you did care about the sum of all of your jail time, then you would encode that in the matrix. All right, so there was a brilliant idea for a game show at one point, and I think some Twitch streamers have done this recently. It was called Split or Steal, and it was a game show. And two contestants chose a ball in front of them. You can see this little ball here, and inside the ball, it opens up, and it has split or steal there. All right, so what you do is they sat two people down in front of each other, and there was a prize of like $100,000, we'll say. Maybe it wasn't $100,000, but it's some amount of money that would be really good to have, right? And so the show was, they're going to create some drama. So they have them sit down in front of each other and tell their life story. Oh, I had cancer. I have kids. My grandmother's sick. I want a new, like, sealed copy of Super Mario 1 or something like that they need money for. And they cry and they go back and forth and all this kind of stuff. But the whole point being that at the end of the show, they reveal their choice, right? So if they both choose split, they each get half the money. If they both choose steal, they both get nothing. If one chooses to split and the other chooses to steal, then the stealer gets it all. So this is a case of the prisoner's dilemma, right? And there's if you go YouTube some clips of this show, two of my favorite ones. So one of them was, it may not have been this exact episode, but it was like, this woman, she's beautiful. This other guy might be single. She flirts with him and makes him fall in love with her and all this kind of stuff. And she convinces him to both choose split. And, I'll go home and take this money to my kids. You can take this money home to like whatever you want to do with it. And they're all hunky-dory. And at the end, she chooses steal and she gets all the money, right? This is what the show was created for, to showcase like the worst part of society or whatever. So in another episode, let me explain. Let me do the next slide before I get to my favorite episode of this, because the game theorist came on the show and like showed how stupid the show was. All right. So in the steal or split, here is the payoff matrix, right? Now, this is assuming, again, that you have assigned a 1-to-1 payoff correlation with the amount of money that you will get, and you are acting greedily and saying, I only care about the amount of money that I get. So here's the payoff matrix for that. If you really cared about the other person, you would assign some sort of value to the payoff matrix for that, okay? So let's do the analysis that we did last time. So let's look at what the other player is going to do. If they choose split, if we choose split, we get half. If we choose steal, we get all of it, right? So steal is better than split if they choose split. If they choose steal, well, if I choose split, I get nothing, right? Because they've stolen from me. And if I choose steal, I get nothing. So they're tied. So in one case, they're tied. And in the other case, stealing is better. So stealing weakly dominates splitting. We talked about strictly dominating before. Now this weakly dominates. So the game creates drama by allowing the players to talk to each other and try and make a deal. And of course, players don't always have this payoff matrix of only caring about themselves. Maybe they do care about the other person, right? So, if it was me and, another person with a family and we talked and I cared about, if I was a decent human being, maybe we both genuinely want each other to go home with half the money. Maybe we genuinely want that. But if we did, we would encode that somewhere in the matrix, right? But we haven't in this case. So my favorite episode of Split or Steal was, so there were two guys, and one guy comes on, and he starts telling his life story and all that kind of thing. And the other guy just stops him, and he says, listen, I'm going to choose steal, okay? So no matter what you say, I'm choosing steal. There is nothing you can say to make me not choose steal. So you have two choices. You can either choose split. If you do choose split, I'm going to give you half of the money that I win. Or you can choose steal, and we'll both get nothing. And he said, either way, this is not the end of the world for me, so you make your decision. And he just sat there with his arms folded. And it was brilliant, right? It's just a brilliant strategy. Now, it turns out that so the other guy started yelling and complaining and all this kind of stuff. And the guy was like, sorry, I'm choosing steal. So the other guy could get no money and if he chooses steal, nobody gets anything. If he chooses split, then he knows he's going to rely on the other person's word to give him half the money. So he didn't, the show starts out by saying, listen, anything said during the game show is not legally binding. So if he promises to give you half the money, he doesn't have to. But if he knows that the other guy is choosing steal, then he has no choice but to choose split in order to possibly get anything. So the guy finally breaks down and says, I hate you, dude, but here you go. Here's the money. Chooses split. And then the guy who was said he was going to choose steal reveals that he actually chose split, right? Just to be a nice guy. But I really loved that episode because it was like, it just showed how stupid the game was, and it was like canceled like a couple of weeks later or something like that. So it's just it's a fun story to talk about when it comes to game theory because it's almost directly related to what we're doing here. All right. So an important note here is that decision-making using game theory assumes that the payoff matrix is accurate for your actual utility. What do I mean by that? Well, for example, if you getting $1 million in life might not be twice as good as having $500,000, right? Like if I got $500,000 right now, that would be amazing. I could like pay off my house. That would be great. Me getting $1 million would not make my life twice as good as if I got $500,000, right? Maybe it's like 1.5 or 1.3 or something like that. But at some point, the amount of money you get, it has diminishing returns, right? So you might assign different payoffs based on that. Like for example, back in the split or steal game, maybe if it was $100,000 versus $50,000 in your personal payoff matrix, maybe you just want to get any amount of money. So getting the 50 is equally as good as getting the 100 for you, right? So just realize that the payoffs are sometimes hard to decide. Maybe an example is you might not care as much about beating the opponent or getting a higher payoff. So direct translation from real life prizes or jail time or grades may not directly translate one-to-one into a payoff matrix, and so correctly choosing your payoff matrix may be difficult, right? Maybe you're super competitive and you want to win the soccer game, or maybe you're a parent in the stands and you just want everyone to have fun, right? So just keep in mind that we're assuming that the payoff matrices have been chosen correctly, but that's a difficult problem. All right. Here's a game we're about to play. This game is called Choosing Numbers, and I play this every year multiple times. Everybody in the class, and currently we're on Twitch, and I currently see around 50 people viewing this live. So everyone in the chat is going to secretly choose a number between 1 and 100. And I'm going to send out a form that you can fill out to choose your number. It's anonymous, right? Please don't troll a bunch of 69s, all right? This is lame. I want the game to work properly, all right? So what it is that you are going to secretly choose a number between 1 and 100. I'm going to calculate the average number chosen for everyone in class, and the winner is going to be the person who chooses closest to 2/3 of the average number chosen. Okay? So, for example, if the average of everything chosen in the class was 60, 2/3 of 60 is 40, and so the person who wins will be the person who chose closest to 40. Similarly, if the average is 30, then the winner will be the person who chose closest to 20. All right? So what's going to happen is, I'm going to send out this form now. I'm going to discard my annotations. I'm going to send out the link. So the link is now in the chat. All right? So you go fill out that Google form. You choose one number. Don't fill it out again. I don't know if I have IP protection or on. Try not to troll it too much. And then, at the end of class, I'll go there and I'll see who won. Now, there's no names there, but just remember what you chose, and I'll say, okay, the person who chose this number won. Alrighty. So that's out there now, and if I can open this up, it's literally just, this is the form. Enter a number between 1 and 100 inclusive. Okay? And so you're going to submit it, and you're going to wait until I show the results for that. Alrighty. So let's go back to the PowerPoint. That is the game. I'll come back to it at the end, and we're going to play it at the beginning of next class too. And in the next class, we'll show you how you can go about decision making for a game like this. All right. I'm going to remove all the troll answers. All right. So just, I'm going to remove them all before I calculate the average. So it doesn't serve you anything. All right. So back to the payoffs, the payoff stuff. So we talked so far about a bunch of greedy people, right? So there's a bunch of greedy people here. Both me and both the other person we were acting greedily. So these were the grades that were obtained in the grades game. So what might a payoff matrix look like for different types of players? For example, what if we had a player that cared about the combination of grades that they and their partner obtained? Okay? What if they cared about that? So in the previous payoff matrix, we just had greedy players. So if they both got a B-, it was neutral. If I got an A and you got a C, I don't care about you. I got my A. Screw off, right? Let's now introduce caring players. So if I get an A and you get a C, that was a 3 because I only care about me. But maybe now that becomes a -1 because I care that you got a bad grade, right? And if I got a C and you got an A, that was now -1, but maybe now that becomes -3 because I'm angry that you chose the thing that made me get a low grade, right? So this is an emotional or a caring player. So if this happens, this is the payoff matrix. So, this was the previous matrix, right? So in this example, this was the greedy one. Both players are greedy and assign higher payoffs to their own grade. They don't factor in what happens to the other player whatsoever. But here is the payoff where people start to care, right? They have some emotions. So this -1 here is going to be the previous 3, maybe -4, because I have some guilt about giving you a bad grade. And maybe now this is a -3, which was a -1, but now we feel kind of angry, so we're going to feel even worse about getting a bad grade. Now, is there a dominated strategy in this matrix? Just quickly do what I showed you before. Is there a strategy that always does better for me, no matter what the other person chooses? So someone asked, in this course, will the payoff matrix always incorporate each player's motivations? So yes, whenever we see a numerical payoff matrix, that has everything factored into it. So once we get to the point of a numerical payoff matrix, okay, all we care about is maximizing values at that point. All right, so everyone's saying no, there's no dominated strategy. And that is true because over here, if my other person is picking alpha, if I choose alpha, I get a 0. If I choose beta, I get -3. So alpha is better when they choose alpha. If they choose beta, I get -1 if I choose alpha, and I get 1 if I choose beta. All right? So that means that beta is better if they choose beta. So nothing is ever always better because one is better in one case, one is better in another case. Maybe, so what would we do here if there's no dominated strategy? Well, this is where game theory starts to, there's nothing dominated, so it can't tell us what to play. So now as a person, we would start to say things like, well, maybe I'll choose beta because beta could give me the best case, right? The best case being I get a 1. But also, beta could give me the worst case of a -3, right? So beta is kind of the high variance choice. It's the risky choice. However, with alpha, maybe you're risk averse and you want to get the best worst case instead of the best case, right? So you'd choose beta if you wanted the best case, but you choose alpha if you wanted the best worst case because with alpha, it's between 0 and -1. So while I can't get this 1, I could only get a 0 in the best case, well, at least I'm not getting -3. Okay? So that just shows you that there's not always a dominated strategy, and you may have to make some decision on your own depending on other factors. So that was with two caring players. What if we are greedy and the other player is caring? Will the choice be different if we know the strategy and payoff of the other player is different? So far we've only been looking at these symmetric payoff matrices where both me and my partner have the exact same payoffs. But what if now we are going to mix a caring player with a greedy player, right? So here's the greedy matrix. Here's the caring matrix. So what we're going to do is on the left-hand side, we're going to have the payoffs for the greedy player. And on the right-hand side, we're going to have the payoffs for the caring player. Okay? So we're going to take these values on the left and these values on the right, and we're going to combine them into this matrix where we're going to have the greedy player on the left and the caring player up top. All right? So as the greedy player, is there a dominated strategy in this game? Okay, that's what we have to ask ourselves. So you can figure that out on your own if you want to pause this, or let's just figure it out in the sake of time. So if the caring player chooses alpha, so we're acting as the greedy player right now. We want to know, as the greedy player, is there a dominated strategy? So if the caring player chooses alpha, alpha is going to do better than beta for me, right? If the caring player chooses beta, alpha is also going to do better for me. Okay, so alpha dominates beta, right? So I chose the greedy player over here, and I know that alpha dominates beta. So let's switch it now so that I'm the caring player, and we'll do the same thing, all right? So if I'm the caring player now, as the caring player, which strategy do I choose? So let's first look and try and calculate, well, if I want to ask which strategy do I choose, I see, is there a dominated strategy? So let's look. Over here, if I'm the caring player, if the greedy player chooses alpha, then alpha gives me 0, beta gives me -3. So alpha is better if they choose alpha. If I am looking at beta for the greedy player, then if I choose alpha, that's actually worse than choosing beta. So alpha's better if they choose alpha, beta's better if they choose beta. Nothing dominates the other, right? So it doesn't tell me what to do. However, if we remember what we just did last time, we know that for the greedy player, alpha dominates beta, right? So if you're the greedy player and you are a rational greedy player, you're always going to do better if you choose alpha. So we know that a rational greedy player will choose alpha, okay? So if we know that they're smart and they're going to choose alpha, right? We know they're going to choose alpha, then we should choose alpha. Because it'd be pretty dumb for them not to choose alpha, right? Because they always do better. So this introduces a new term. Our best response to the greedy player's selection of alpha is for us to choose alpha. So the best response is always to a particular choice of the other player. So our best response to alpha is alpha. Our best response to beta would be beta, okay? But we know greedy will choose alpha. And so what we have to do sometimes in life is put yourself in the other person's shoes to figure out first what they're going to do. So if the other person has a dominated strategy, you know they're not going to pick the dominated strategy. They're going to pick the other thing, right? So all you need to do is look at what you're going to do if they pick that other thing. So put yourself in the other person's shoes to try and figure out what they'll do. And this gets to me at some point. This explains so much about life, right? Where you're always like, if you're playing a game or something happens in life and like someone does something that disadvantages you, you get super mad at them. But if you just look at why they made that decision, it's probably very easy to understand because it advantaged them to do it, right? So the other person is caring about them, you're caring about you, and so you can't get mad at someone else for being greedy if you're also being greedy, right? So try and put yourself in the shoes of the other person to figure out why they made their decision. That will tell you what their decision is, and then you can best respond to that decision. So best responses. Now we have this term that we're going to look at in a little bit more detail. So the strategy which performs best against a given other strategy is a best response. So in the previous example, we knew that the other person had a best choice. So we choose our best response to it. And Sun Tzu in The Art of War says, to know your enemy, you must become your enemy, right? So you become your enemy, you think what they would do, and then you make your choice based on that. Someone in the chat just asked, is this similar to Minimax? So you're either very smart or you saw the beginning where in 2 lectures from now, we'll talk about the Minimax algorithm and how that ties all back into this. But yes, the best response is the key to the Minimax algorithm. All right, so what makes a game? If we want to enumerate it in a sort of exam question-y sort of way, what we have in a game is we have a set of players. So players are going to be I, J, K, whatever. And that is you, it's the other player, it's whatever, okay? We're going to have a strategy, SI, and so that's a particular strategy. So if we are looking at this example from the point of view of the numbers game, all right? So the numbers game that we played, that form that I sent out, picking a number between 1 and 100. So a strategy would be a particular strategy of player I. That's SI. So the strategy of I, if you're player I, is the number that you chose. So for example, maybe I'm player I, and I chose 13, then SI would be 13. Now, there's another thing called big SI, and that's the set of all possible strategies for a particular player, right? So big SI would be all the numbers from 1 to 100. S, that's the strategy profile. So the strategy profile is a set of choices for everyone in the game. So in the grades game, a strategy profile would be player 1 chose alpha, player 2 chose beta. That collection itself is a strategy profile. For the numbers game, the strategy profile would be all of the sheets that you handed in if this was in person, or it would be all of the form responses that you gave to the document that I handed out. S minus I would denote the choices for everyone except player I. Okay? And we're gonna use all of these variables here to give like mathematical definitions of best response and stuff. So that's what this is all for. And the payoff, or the utility, so U sub I of S is the utility or payoff for player I given all of the choices of everybody in the game. Okay? So U sub I of S is essentially the cell entry in the table. And in one offering of the course, I gave $5 to the person who was closest, right? So that was, you either got $5 for winning or you got nothing. And you're all online, so I'm not sending you $5, right? Maybe I could send you like trillionth of a Bitcoin or something. But anyway, we don't need monetary, monetary, what do you call it? Incentive to play these games. And so you're going to assume all of these are known values. Okay, let's move on to another example of another game. So here is another matrix. We have player 1, we have player 2. So let's put this game in terms of this terminology now, all right? So we have players 1 and players 2, right? So we call them player 1 and player 2, but they could also be player I and player J, right? Player 1 and player 2. Here are the strategy sets. So S1 is the strategy set for player 1. So, the strategy set for player 1 is top or bottom. So LCR, left, center, right, T, B, top or bottom. I've just chosen these arbitrarily to like mean something in the real world. The strategy set for player 2 is LCR, which means left, center, right. So just some example payoffs. An example payoff. So the utility for player 1 of player 1 choosing top and player 2 choosing center. So here we go, player 1 choosing top, player 2 choosing center. It's the first one, so it's 11. Here, for another utility could be utility for player 2, where player 1 chooses bottom and player 2 chooses left. So down here, bottom and left. Alrighty, so that's how you would take a game that's shown in tabular form and translate it into this more mathematical nomenclature form, right? Cool. So for this example, does player 1 have a dominated strategy? So I want you to take a minute and look at this and say and answer in the chat if player 1 has a dominated strategy. And again, that means you go over all of the choices for player 2. For each of them, you look at all the choices for player 1. And if something is always better than something else for player 1, then it has a dominated strategy. Okay, so I got a couple of no's out there. That is correct. There is no dominated strategy for player 1. So we figured that out by looking at, okay, for left, B is better. For center, top is better. Done. Because if they're not always better, then we don't even need to look at right. Because top was better for one, bottom was better for another, so nothing dominates the other. Does player 2 have a dominated strategy? Now, I'm not flipping the matrix, so this is your mental exercise to look at what player 2 does, right? Does player 2 have a dominated strategy? And I'll ask that again. And we haven't done it from this direction before. And we also haven't done it with 3 actions before. So I've got 1 yes, I've got a couple of no's, I've got another yes, split 50-50. All right, let's explain it. Yes, it does. C dominates R. Look at this. So if we fix player 1 as choosing top, C is better than R, right? Oh, sorry. C is 3 because we're looking at the second ones now. So if we fix player 1 as T, the choice of C for player 2 gives 3, and it gives a 0 for R. So C is better than R when player 1 chooses T. For B now, C gets 2 and R gets 0. So C is always better than R. It dominates R, okay? So just keep in mind that not everything has to dominate it, right? So for example, L doesn't also dominate R, but C does dominate R. So does there exist any strategy for player 2 which always does better than any other strategy? All right? So that's not always intuitive at first glance. So the moral of the story here is that if we look at it, C always performs better than R, so we would never choose R. That's the only thing we take away from here. I'm not saying that you should choose C. I'm saying that you should never choose R. There's a big difference there. All right. So we're going to look at like the mathematical definition of a dominated strategy now. So player I's strategy, SI prime, okay, is strictly dominated by player I's strategy SI if the utility for player I choosing SI when the other player chooses, where all the other players make all their choices, so that's for every possible choice. So the utility for players I for every possible choice choosing SI is bigger than the utility for player I of choosing SI prime. So SI prime is dominated if SI is always better. That's what this is saying. For all S minus I, meaning for all strategies except the choice of player one's I. Great exam question there. All right, one more game. Maybe there's another one. I'm not sure. I think this is the last one. You are a general defending a city. Okay? You have an army, and the attacker has 2 armies. There's 2 paths leading into the city. There's the easy path and the hard path. You have to make the choice to only defend one of these paths. All right? If the attacker chooses the hard path, it's going to be like through a mountain range. Okay? So just by choosing the hard path, they are going to lose 1 army. If your armies meet, the attacker loses 1 army. And the enemy wants to maximize the number of armies in the city, and you want to minimize the number of armies in the city, okay? Or maximize the number of armies that you kill. So here's what this looks like as sort of an illustration, right? So you've got this base, you're sitting here in the base, right? And you have to make a decision. Do you put your army at the easy path to defend there, where all the flowers are growing? Or do you put your army at the hard path? Okay? So the enemy is going to start out with 2 armies, and they have to choose one of these paths. If the enemy chooses the hard path, they are going to, like, one of their armies is going to die of starvation or cold or whatever. So you know that only 1 army will be making it via the hard path. So where do you put it? Okay? Do you defend at the easy path? Do you defend at the hard path? So let's do this. That might be an actual decision that you have to make in a video game. Or if you happen to become like Genghis Khan, maybe you will have to make a decision like this, right? So good luck if you become Genghis Khan, but you could use game theory to solve your army placement strategies for you. So let's look at the defense game here. If I choose easy, yeah, there's different pronunciations. I'm sorry if I mispronounced Genghis Khan. So if I choose easy and the attacker chooses easy, if I'm the defender, right? The defender, if we both choose easy, then the defender's value is how many armies that they killed. Because if we both chose to put armies in the same place, they fight and each player loses an army, okay? So if we both choose easy, well, the attacker is going to arrive at the city with 2 armies, right? Because they haven't lost 1. So they've arrived with 2, I've killed 1, and so this 1 here means how many armies of the attacker made it into the city. Perfect. If I chose easy and the attacker chose hard, then our armies have not met, and so all of the enemy armies make it into the city. However, they lost one of their armies by going through the hard path. Okay? So in that case, the enemy has lost 1 army by going through the hard path, but they've also made it into the city with 1 of their armies. Now, if I choose to defend hard as a defender, if the enemy went easy, well, that's the worst possible case, right? Because if I chose to defend hard and they come through easy, I haven't killed any of their armies and they've made it into the base with 2 of their armies, which is brutal. But if I choose to defend hard and they choose to defend and they choose to attack hard, then one of their armies is lost because it's the hard path, and another of their armies is lost because I killed them, right? Because we met. So in that case, I've killed 2 of their armies, and 0 of their armies have made it into the city. So the attacker payoff is the armies that have reached the city. The defense payoff is the attacking armies killed. And the question here is, does the defense have a dominated strategy? Okay, so does the defense have a dominated strategy? All right, let's look. If the attacker chooses easy, well, my choices are, if I choose easy, okay, I get 1, they get 0. If the attacker chooses hard, I get 1 or 2. So in one case, I do better, right? If the attacker chooses easy, easy for me is better. If the attacker chooses hard, then hard is better, all right? So no, the defense does not have a dominated strategy. So I can't just say one of these is always better. Does the attacker have a dominated strategy, right? So to look at the attacker's options, we have to fix the defender's options. So in the case of the defender choosing easy, well, easy and hard attacking are going to be the same value, okay? So if the defender chooses hard, then choosing easy is going to be better than choosing hard. So easy weakly dominates hard in that it will do at least as well, or better than hard. So this means that, and again, the definition of a weakly dominated strategy is that instead of a strictly dominated strategy where it always does better, it means that it does at least as well in everything, but it does better in something, okay? So in this example, it did at least as well in everything, but it does better in something. So that's what the weakly dominates is. So you probably shouldn't play a weakly dominated strategy, all right? It's not always guaranteed to do worse, but playing the other one will always do at least as well. So you probably shouldn't play a weakly dominated strategy. So in that case, if in the attacker's case, if we fix, right? So what was it for the attacker? Easy weakly dominates hard for the attacker. So that means if you know the attacker easy weakly dominates hard, then you know that they will be choosing easy, right? And so if you know they'll be choosing easy, then you defend easy. So that is the game theoretical way of approaching this situation. Okay? So hopefully that is enough to convince you that game theory it's a good way of, once you have payoff matrices, to make that decision. So just as a recap for today's class, okay? So games have players, strategies, and payoffs. Players want to maximize their payoff or maximize their utility. A strategy dominates another one if it is always better, strictly dominating, or as good, weakly dominating, to choose it. You never play a dominated strategy. And if there is no overall strategy to play, consider the other places. If there's no overall dominated strategy, so you don't know which one to pick, consider the other player's best choice first. And if the other player does have a best choice, you pick their best response to it. Okay? So some possible exam questions here would be, given a payoff matrix, compute the dominated or dominating strategies, explain why the choice of strategy is good or bad for a given matrix, compute the best response to something, or construct payoff matrices so that a given strategy dominates another, etc. So there's lots of cool exam questions that you can ask for this topic. All right, so that's the end of Game Theory Part 1. And what I'm going to do now is I'm going to go to the Google form, and I'm going to look at the responses, and I'm going to calculate the winner. So let me go do that. Here we go. I gotta go to my Google Drive to get that. Just give me a second. Numbers game. 37 responses. Okay, let me generate a spreadsheet of those responses. Here are the responses. I'm taking out the trolls, so I'm taking out all the 100s and all the 69s. Thank you for intentionally trolling the game. All right, okay. So here are the values that were given. And so now I'm going to say this equals average, okay, of this to this. So the average value chosen was 28.75. And if I say this equals this times 2 divided by 3, then that is 2/3 of the average. I didn't mean to delete that. So that means that if anyone chose closest to 19, they will be the winner. So here is, let's see, 22 is 3 away, 16 is 3 away, 17. We've got a 20, a 20. We've got no 19s, but we do have 1, 2, 3 20s. Okay? So these 20s won. So if this was in class, you would be getting the $20. All right? Or the prize, whatever that was. Okay. Yeah, no, this is just the defaults. This is, I am on a 1440p screen, so I apologize for the screen, the font size. But yeah, so that is the numbers game. And I'm going to let you think about the numbers game, and we're going to play it next time. And what do you think will happen to this value when we play it the next time? And then the next time, and then the next time, and the next time. Okay? And we're going to mathematically show why that is. And we're also going to talk about some other cool stuff. So in the next lecture, we're going to be doing the rest of game theory. Then we have midterm break after that, and then we're going to talk about Minimax. And then October 19th, okay? So 2 weeks from today is the midterm, and remember that that's on campus, all right? So that is a physically written midterm. So just remember that that's creeping up on us. Alrighty, thank you very much for tuning in today, and I'll see you on the next one.